Unit 4 Chemistry, looking now in volumetric analysis still, but at how we can analyse organic acids and bases through volumetric analysis. So let's remember first what an acid is and what a base is. Okay? An acid is something that donates a proton, a base is something that accepts it. So this red dot is my little proton, which is moving from one side to another. Conjugate acid-base pairs, like these, are ones which differ just by a proton. So HCl is an acid, its conjugate base is Cl-. H2O here is acting as a base, it accepts a proton and becomes H3O+. Okay, so there are two pairs for a reaction, and any acid-base reaction is going to have two conjugate pairs. Okay. Similarly in this reaction, nitric acid dissolving in water, we've got a conjugate acid of water being H3O+, and the conjugate base of nitric acid being NO3-. And there's another example there. In this instance, water is acting as the acid rather than as the base, and we make hydroxide ions as its conjugate base. If we're doing these sorts of analyses, we need to be able to calculate pH. And pH, remember, is the concentration of the hydronium, the H3O+ ion, in solution. Okay, it's a logarithmic scale, so pH is negative log of H3O+. And at 25 degrees C, those two multiplied by each other are equal to 10 to the negative 14. If we've got a basic solution, we would normally use the pOH or the concentration of hydroxide to then work out the pH using this relationship. Okay? So my preferred way would be to use OH minus, negative log it to find the pOH, and then we know that pOH plus pH equals 14, so I can find the pH by doing 14 minus the pOH. Okay. Alternatively, you can use this relationship here, so from the concentration of hydroxide ions, you can find the concentration of hydrogen ions, and then hydrogen ions, you can find the pH. Either way, you've got to do two steps. Personally, I think this step is easier than that step, which is why I go that way. Now, in organic acids and bases, we've got carboxyl groups. Carboxyl groups are weakly acidic, so it's the hydrogen of the COOH group that is donated. If there's more than one COOH group, then they'll donate more than one proton, but those that are just in CH2s or CH3s do not. Amine groups are weakly basic. They can accept a proton to become NH3 positive. Okay? So therefore, because we've got acids and basic groups, we can use volumetric analysis to find the concentration of these weak acids and bases in a solution. In order to do this, we're going to have to use an indicator, because acids and bases themselves don't have a natural colour change. Okay? These themselves are weak acids and bases, and they will change colour when we add or remove protons from them. Okay? Lots of them are naturally occurring, and we don't use a mixture like universal indicator. We use a particular indicator that's going to change at the right point. Okay? So your data book has not a pictorial version, but details of these, as is your data book had in year 11 as well. So it would indicate the range at which it changes colour. Okay? Anything below that range, it would be in its acid colour, so bromothymol blue would be yellow, and then it changes to blue at around about pH 7, whereas something like methyl orange changes at a much lower pH, a pH of 3. Okay? If we are using indicators in a volumetric analysis, then we know that we're going to have acid plus base gives you salt plus water. Okay? What we need to do is have an indicator which changes at an equivalence point, at close to the equivalence point. The equivalence point, remember, is when they're in stoichiometric ratios. To do that, we need to think about when that equivalence is going to be. So if you have a strong acid and an equally strong base, your equivalence point is going to be 7. Okay? But as we just spoke about, neither organic acids nor organic bases are strong. So what you're going to have instead, potentially, if you're analysing an amine, is a strong acid that would react with it, and the weak base, which is your organic acid. Okay? In this case, the organic acid is sitting in your conical flask, which we can tell because that's where also our pH detector is going to be. And we're titrating in an acid. Because the acid is stronger than the base, one of the products is also going to be a weak acid. So our equivalence point is going to be in the range 3 to 7. So we need to look at our indicators and choose something that changes in a similar range to that. If we're looking at a carboxylic acid, it's going to be the opposite. We'll have a weak acid and a strong base. Okay? Therefore, we're going to have a product which is weakly basic. So our equivalence point is going to be something between 7 and 11, around about 9ish. Okay? That means we need to choose an indicator like phenolphthalein or something similar to that, which will change in that range. Okay? What we're not going to do ever is titrate a weak acid against a weak base, because we don't get a nice sharp slope like we get here. So if we look at this one, we're going to find that we wouldn't know when it changed. Given they've all got a range, if it changed here instead of there, the difference in volume that you're adding is too small. So we always have to have either a strong acid or a strong base in our titration.